Give me the TLDR. And the TLDR of the TLDR?
It's hard to run things concurrently, and now we can do it.
With MCP.
With MCP.
Great. So let's dive deep into the episode.
We're doing exploratory execution. We're just letting the agent play. We're letting the agent explore, because in their heart they are kind of like random beasts. So now we want different sub-agents to kind of work on the same problem, but side by side, in parallel, because we don't want to wait. We don't want to do it sequentially. It will take too long. So now we're trying to solve the same thing in parallel 8 times or 16 times. And it's easy when all we try to do is like read tasks. If we're not mutating anything, then that kind of lends itself to parallelism very well, because everybody can just read. But the real challenges happened when we try to alter state. And we really stumbled into it quickly when we took our system, Maestro, from like read tasks to write tasks when we tried experimenting with coding. Coding, you need to edit files, you need to add dependencies. You have a lot of shared resources that all agents are working on concurrently. So if I have a very simple thing, I want to say one of the first things we tried to do, we told it, write me a Tetris program. So the first thing it does, it creates a file, Tetris Python, Tetris Py, and it tries to implement the Tetris code. And now you have 16 agents trying to write the same agent and add some dependencies maybe and things like that. And we ended up getting conflicts. So we said, okay, we can't let this happen. They're not going to coexist unless we create some sort of isolation. And when you talk about isolation, you need to be isolated in terms of the runtime of the sub-agent and also its tool use. And when we talk about tool use, that's where MCP comes into the picture. And MCP allowed them to kind of do our tool use. For us, it was just making bash calls, but you can imagine different coding-related tools. There are some others. But just calling the bash tool, that's what agents do best. They kind of do all stuff of like really raw grepping and ls and stuff like file system-related stuff in order to author their code. So when we didn't have isolation, we saw them start to step over each other when they tried to, like, someone would add a line, another agent would delete that line and rewrite everything. And we ended up getting like very bad results because essentially the final, just the slowest agent would win. They would overwrite everything.
Is it something that's really that common? Like I see a lot of deep research agents, see a lot of what you call read-only agents or something like that. Do we really need agents to do a lot of tasks?
Yeah, so even deep research, it's a great example. Deep research kind of inherently sounds like it's read-only. But when you have a very long horizon task, when the agents do a lot of running, they have to save some interim state. And here, even like as an artifact of their work, they need something to mutate. And you may want to share this state. Like this is the whole concept. If you want some shared resources. So at some point you do deep research, your context explodes, you want to do some compaction, you want to say, this is what I know of the world. You know, the agent, a lot of times you take a task, you tell it, figure something out, and then share your findings here. And you have different sub-agents that kind of share their view of the world. That's how you solve the very complicated problems. So you can see even if you use Cursor or some Cloud Code or things like that to do intensive tasks, they would eventually kind of spew out, say, here's my thoughts, and I save them in like overview.md. And then they re-reference their interim state as they go along. So it is quite common. Like for us, we saw a lot of different benchmarks that would face the same issue. A lot of tool calling around things that are mutatable. Like anytime you want to write anything, you're in this domain where you're mutating state.
So what breaks when agents start writing and changing states, and how does MCP help standardize that?
So I think it's the implementation has a lot of complexities and it's very interesting, but the concept, the problem it's trying to solve is fairly straightforward because we're just allowing agents to access tools. And the concept here is that it deals the standardization. It's like the USB-C of tool calling. because you want all the different agents to have some common interface. So to get back to where we started seeing the protocol like come to some limitation. Seeing MCP, as we said, it says what the agent can call, what tools, what capabilities. But it's not talking about the where. It's not talking about where this thing is going to run. So when we expose a tool, we're saying if we're doing it the most simplistic way, we're kind of assuming a shared environment. We're saying, okay, right, we can write files, so ask us to write files. And we're not leaving, like, you should leave either the model or even take care of it as part of your own system, the question of where we want to run the code or run the tool. So that's what we found was missing. And once you start kind of understanding that something is lacking, you start seeing more occurrences of this problem. And for example, when we were working on this problem, just after we landed on our solution, the Cursor team came up with Cursor 2.0, and they said we have multi-agents. You can send the same coding problem to different models and see how they interact. To do that, we created our own isolation so every sub-agent can work in separation. And you say, oh, that's interesting because they're dealing with the same thing. And then we saw the guidelines of working with Cloud Code, and they said if you want to run multiple occurrences of Cloud Code, then create your own copy of the code base and then run your sub-agent there.
So essentially it's something that every coding agent right now, or at least the lead coding agents are doing, and you're just standardizing this.
But they're saying, let's take this complexity out of the system. You need to provide the isolated environment and then let us run inside this environment. So it's not just the standardization, it's also bringing it into a part of the protocol. Say, okay, if everybody needs to address this when they're doing writable context, then we should let the protocol handle it for them.
Yeah.
So simplistically, you can say, all right, let's say that let's go back to our coding example, and we're saying we want to run code. So let's just add the where we want to run it. So we can say, whereas before I sent the command I want to run as the only parameter, now I'll give some notion of isolation. So let's say we set up this notion of workspaces, which is kind of the terminology that we ended up on. And we'll say, let's pass a workspace identifier, and we'll pass the command. And technically, that's all you need to add. We'll soon talk about like the actual constructs that we chose to implement in the protocol. But that's all you need to add in case you kind of trust the model to make these decisions on their own, which is the industry standard a lot of times. Because you remember MCP, we say that the agent halts with the right parameters to make the call. So the agent knows, for example, they want to list files. So maybe they can also know that they want to isolate, right? But we're kind of bringing some more complexity to the agent. We didn't want to do that because we weren't sure that we're going to get the right behavior from the agents. And in the Maestro system, we kind of took a very principled approach of separating between the orchestration and the actual agent logic. So for us, it was very clear that we should handle it in the orchestration layer. So we made modifications to our system to handle the workspace isolation, triggering and passing the parameters as outside the scope of the agent. So the agent kind of doesn't know that it's being isolated, but our system ensures that we're kind of setting them on the right track. So we're essentially automatically doing what Cursor and Cloud Code instructed their users to do, but we're setting our agent, our sub-agents in the right path.
Kind of sounding like when you don't want a sheep to be scared.
Yeah.
So you're not telling it something bad's going to happen.
Exactly. We're just saying, okay, we just, when we send their agent off to their merry way, we're just saying, okay, you just start your exploration from here, and we make sure there are clear boundaries between our sub-agents.
Okay, let's make it a bit more concrete using an example. You said we only have to pass the workspace. What does it mean for coding agents?
Yeah, so great. For coding, when we're doing, let's take our Tetris example, the toy example. We just want to create a file, right? So we have our initial code base, and we want each sub-agent to have a fresh copy of the code base. And here, so we're saying, let's do some initialize for the workspace. We'll set a fresh version. So when actually, before we even interact with the coding agent, we may have it's called a dirty state of the repository. Maybe it's not as bad as it sounds. It just means that, when we work with Git, when we work with code, we have some source control. And at some points we have checkpoints. We're saying this is a steady state I like. We give it some name. It gets some numbers, right? And I can go back to this state in case I make some catastrophic error, right? So if I I leave this steady state, deviate from the steady state, then it's called a dirty state. And maybe I don't want to be in the dirty state. I want to let the agent kind of start off in a clean state so they can roll back to it all the time. So that's our first contract. We call it init. We're saying we're taking the current state of the repository and we're creating a fresh version of it. And that's going to be the starting point for our main agent. So Codebase is basically just files. And on top of that, we have a layer of some source control, so Git in our case. So like one way you could isolate is you could just copy all the files. You can take all your working directory and copy everything to another directory, and then you're isolated. Everybody works separately.
That sounds naive but wasteful.
It's a bit wasteful because there are some things that that are shared between the code base, and you don't, like, for example, all the packages that you have when you're writing code, you have dependencies. So maybe I want to do something nice with graphics, and then that may be a heavy package and I don't want to duplicate it. So Git kind of has its own way of standardizing what we do need to duplicate and don't need to duplicate. And they also did a nice integration between that and folders, and it's called Git work trees, and that's what we ended up using. And also we saw afterwards that that's the recommendation. After we landed on the decision, that's the end recommendation of the cursor teams and also Cloud Code. So we felt confident with this trade-off. Other alternatives could be when we ran our agents, like the code ended up being on a Docker container. So you could think about just spinning up a new Docker container. That's even, it's not only the file base, it's the entire OS. You're just letting it run it completely sandbox. We'll go over a few of the other constructs, and then we'll see that actually a lot of systems that deal with writing also have some inherent concepts of isolation, because it's not that if it was the fact that just we lucked out by landing on coding and Git work trees, and that's the only kind of infrastructure that lends itself to isolation, then it would be kind of a weak takeaway. But we actually looked at different alternatives, and we see that all of them have the relevant constructs that you need. So we said after cloning, every sub-agent now has its own isolated space, and they can do all of the impressive stuff. At some point, we're saying that the agent or the system kind of concluded its work, and then we want to do two things. One, we want to check the difference between its current state and its origin state. So that's for us in order to make the actual decisions afterwards of which one is the best.
Kind of like a diff.
Exactly, a diff. And it's the underlying command is the diff command.
Okay.
And then also at some point you want to integrate the sub-agent changes into your code base, so that's
merge. That's merge.
Exactly. And then to clean up all the sub-agents that didn't end up making the cut, delete, right?
How original.
Yeah, but we didn't have to reinvent everything. But we just saw that just making this connection between the primitives and the workspace, now our system kind of sets everything up on behalf of the sub-agents. So what happens, like if we do a flow diagram, we start running, at some point we understand we want to create a few sub-agents. So the side system in charge of isolation does the cloning and creates a workspace ID for every sub-agent. At this point, the sub-agent now wants to make a tool call. And that's, for us, the most interesting part. If you remember when I said the first alternative is we need to add the ID into the tool call. And then it's kind of the agent's responsibility to know that it needs to generate this ID. And they kind of need to do all the heavy lifting of keeping all the workspaces in context and understanding which workspace should be used to run which command. For us, since we separated the orchestration to a different layer, we inject the workspace ID automatically on behalf of the sub-agent. So when they do their tool call, they're just saying run the list files command. our system gets this kind of intercepts this command, and this is something that we did in the MCP client side. And we're saying, okay, we know this sub-agent is part of a workspace like 123. So we inject the parameter, run this command on workspace 123. And then let's complete the entire end-to-end. So now our system knows that the workspace is just like a theoretical abstraction. It's saying, okay, that actually maps to this folder in the file system that was mapped using Git work trees. And then we run the list files on that folder. So now if one agent in a different workspace lists the file, it sees its view, and another sub-agent sees its view. If they both try to kind of modify the same file, each modify their own copy of the file. When they're done working, we pick the winning agent. Their file gets merged into the main code base, which, as you remember, is a clean version. So it didn't corrupt anything, our original work. And then we delete everything, so nothing we don't have any leaks or any resources. We keep it very efficient. So if we look from the outside view in the system, it was able to experiment, do like 16 iterations of trying the same thing. And then when we see the end result, we got the best one, and it looks like everything is the same, right? Our code base didn't get corrupted. Everything happened side by side, but the end result is what we want.
All because of improvements of MCP.
Yeah, we saw a missing capability. Mm-hmm. So we needed to add, but it's two things. One is just like the constructs of isolation. Mm-hmm. So now it means that even if we work in different domains, we just need to change our workspace implementation. Even if we ended up, we would identify, let's say, a bottleneck that Git work trees wasn't able to address, we could change our isolation implementation of saying, let's do isolation using like spinning up new Docker pods for every sub-agent. And the code would be the same. The agent doesn't need to know about the isolation implementation. They just say, I want to run this code. And for us, we just know how to route the workspace requests to the different workspace management system, right? And we ended up implementing all of these pieces. And then when we talked about cross-domain, like multiple domains, now you understand that the same agent using the same tool, now if you provide it some means of, let's say, interacting with the document, then it can do mutations on documents without conflicting.
So this is what you would say to someone who says, well, I have a problem where I have multiple agents or multiple sub-agents that needs to write. What do I do?
Yeah. So if let's say, so first you need to analyze your domain, and you need to map the constructs that we defined to your problem domain. You need to implement them. And then the first thing before, like if you don't need to even separate the orchestration between the agent run, the first thing you can do is to actually add the workspace ID to your to your tool calls and see if the model can kind of carry all this heavy lifting for itself. Maybe it can for your use case, right? That means that it's the model's responsibility to kind of keep track of the workspaces. They should know when, the model should know when to isolate and to make multiple calls with the same ID when it makes sense. If that doesn't work, then we recommend separating between the orchestration layer and the agent layer. And that means that you need to take care of making sure your agents run in the appropriate workspaces. So you need to take care of that. That means that you hide the workspace ID from the tool calls. You don't pass the parameters. Your infrastructure or your part of your system that's in charge of triggering the sub-agents, it's its responsibility to pass the workspace ID. But it's not something that's very complex. It's just some engineering work to separate these concerns.
Yeah, I get it. I think that's really cool to really take this, extension for the MCP protocol and, leaving the complexity out of agents who are already, I think, very complex systems as they are. How much did you actually manage to scale with that?
Yeah, so when we created our system, when we did the coding modification, we targeted a benchmark called SweBench. And it kind of deals with like hard coding issues. And a typical run in SweBench could take about an hour. So if you're only able to run one strategy at a time because you're doing mutations, then you're spending an hour. And if you need to do 16 of them, it takes 16 hours. we were able to parallelize all of our attempts. So all strategies that we wanted to try, we did in the same time. So we ended up landing on 16, but you could go however big you want, because the MCP and the isolation is not really a bottleneck. Its resource usage is almost negligible. So you get for us, it was a 16x time reduction, but it could be as many scales with as many strategies as you want to try in parallel.
And still only take 1 hour.
Yeah. It takes as your longest strategy. So for example, smaller models may finish before the longer models.
Okay. And what's in store for this extension of MCP? What's to come?
Well, for us right now, one thing we want to stress is that even if you're only running a single agent, we saw as part of our experimentation that it makes sense to run it multiple times. So even if you have just a single strategy, the fact that you're fanning out, that you're trying it multiple times, we think is going to be a very key part of agentic strategies moving forward. So we have our benchmark, our framework in place to handle this, and we hope to kind of we detailed our findings in our blog, which is now available, and we really hope to see some community adoption, because we feel like this challenges us with some of the extreme use cases that are going to start popping up more naturally in the upcoming months, and we kind of want to share how we handle them, and we hope to get some feedback from the community and see if it works, if it solves some of their problems. And also we're kind of heading into more benchmarks, and we want to double down on this approach and see if it generalizes well.
Cool. Hopefully in the next release of MCP, this will be part of the official protocol.
We hope so, and we're reaching out with the MCP teams to see if we can integrate it into their protocol.
Oh, thank you so much for coming here. I think you really took MCP and put it in very clear order for me. I feel that I can now say that I understand MCP, which is something I haven't been able to do for like a year. So thank you very much. And for the rest of us, stay tuned for other episodes of YAAP.